Now in this video we're going to look at capacitance. We're going to do so by working out a problem on capacitance and thereby applying the formulae for capacitors in series, capacitors in parallel. The paper that I've used for this video is the November 2020 paper 41, that is question number 6, and it is in the 9702 physics syllabus. Now, before we go any further, please remember to subscribe to the channel, as well as like and share and comment, as well as hitting the notification bell so that you get alerted of my future videos. Without much further ado, let's get started. Now, this is the November 2020 paper 41, question number 6. Part A and part little 1 says that define capacitance of a parallel plate capacitor. So you should be very careful of the words here. Some people may confuse this word parallel plate capacitor and think that we're talking of capacitors in parallel. No, this is just a parallel plate capacitor, and this is the ratio of the charge stored on one of the plates to the PD across the plates. So the ratio of the charge stored on one of the plates to the PD across them. So the fact that you write the ratio of charge stored to the PD, you get 1 mark. And then now to state that it's the charge is stored on one of the plates, and then the PD is across the two plates, you get the 2 marks. Okay, so the ratio of the charge stored, so this is supposed to be charge. So ratio of the charge stored on one of the plates to the PD across the plates, 2 marks for that. Now then the little 2 says state 3 functions of a capacitor in electrical circuits. The major ones that should come up to your mind is the smoothing. Remember, when you convert AC to DC, you use diodes. Then after that, you need to connect a capacitor in parallel with the load so that you smooth the DC signal. The other one that should come to your mind is the blocking DC. So if you want to block DC, you use a capacitor. Also, time delay circuits. So all time delay circuits do have a capacitor in it, because as the capacitor discharges, you're going to be having a time delay during the discharge process. Others that you could think of: tuning circuits, oscillator circuits, surge protection. Also, we have a capacitor in there. And also, you know that capacitor provides temporary charge in the circuit, or temporary current or temporary power in the circuit. But the major 3 that should come to your mind right away should be these ones that I've written down: smoothing, blocking DC, and time delay circuits. Now moving on to the question now that requires the calculation. Says the capacitors are connected as shown in figure 6.1. So we have got those capacitors. Now the question wants you to find the combined capacitance between the terminals X and Y. Now you need to understand how these capacitors are connected first of all. So you have got a junction over here, and then you've got a junction over here. So all these capacitors, these 3 capacitors, as you can see, they don't have a junction, so which means they've got the same charge flowing through them. So you can rearrange them to be like this. Okay, so these are in series. That's what it means. And then the junction now is been across that. So we've got it like this. So X is here and Y is there. So which means that these three capacitors, 24 microfarad capacitors, all these are connected in series and then in parallel with the other 24 microfarad capacitors. I hope you understand how I managed to come up with the three capacitors in series, but as you can see, there's only one path of flow of current in the three. So that's why we say that these are in series. Now to get capacitors in series, the total capacitance in series is given by 1 over C1, or 1 over CT is equal to 1 over C1 plus 1 over C2 plus 1 over C3. So capacitors in series behave like resistors in parallel. So in this case, it's going to be 1 over 24 by 3. So 1 over 24 plus 1 over 24 plus 1 over 24, which is 3 over 24. Which means that to get CT in series will be equal to the inverse, which is 24 over 3, which gives you 8 microfarad. Okay. Now, this is now equivalent to having two capacitors in parallel, which are the 8 micro that we have found from capacitors in in series, and then the 24 micro, which is there between X and Y. So capacitors in parallel, they behave like resistors in series. Okay, so we simply add the resistances. So the combined total that is in parallel will be equal to the 8 plus the 24 micro, which should give you 32 microfarads. Okay, so that's 32 microfarads. I hope you have understood the way I've come up with the network of resistors in series and the way that I've used the formulas to find capacitors in series and capacitors in parallel. Please don't forget to like, share and comment, as well as to subscribe to the channel Physics Tips for Cambridge Students YouTube channel. Signing out.